Hi everyone, welcome to this video where we've been learning about the concept on elements, compounds and mixtures. Now this is pretty similar to what you have learned before in lower sec, so you'll realize that most of the contents remain the same. Right? What is only the main thing that you need to take note of for upper sec is that there is now a lot more focus on particles. Right? So as you learned in the previous chapter on kinetic particle theory, you realize that all the substances in the world are made out of what we call tiny particles. Right? So as we go into elements, compounds, and mixtures, likewise, you're gonna look at that. So before we start off with this entire chapter, I just want to introduce all of you to this concept called the macro, submicro, and representational levels of understanding in terms of chemistry. Now, seems very complicated, but let's take a look at what it means. Macro means what you can actually see, touch, or smell. So for example, if you look around the class right now, the paper, the air around you, the wind, the smell of something that's going to your nose, these are all called macro. These are all observations that you can see. The table, the notes, the paper, the PLD. Now, submicro means to look at things in terms of the particles now. Now, you know that actually all the substances around us is made of particles, as mentioned. So, when you think about particles, you need to know that it can be in terms of atoms, ions, or molecules. Yep. And then we go on to representational. Now, what exactly is representational? Representational is when we use a symbol to represent what the chemical looks like. So let's take a look at water, for instance. Now, a beaker of water in front of you just looks like water, right? It's just a cup or a beaker of liquid, right? So that is what we call macro. Now, in terms of submicro, what it means is that water is actually made of water molecules. As you can see over here, the water molecules are represented by these three circles, where one is red and two is white. This doesn't mean that it's really this color, it's just there to show you what it will look like. And then from there, so from macro to submicro, and what does it mean when we say representational? Representational is where we write chemical formula, right? So instead of drawing out the model, we actually write H2O, and that will represent water, right? So the boiling process is represented by H2O bracket L to represent liquid, and an arrow to H2O bracket G to represent gas. So that would just be a quick snapshot in terms of what it looks like as we go into this chapter where we're learning about things in terms of the particles, right? So for today, the first part of this video, we're actually going to look at this macro aspect. So we're going to recap about elements, we're going to recap about compounds, we're going to recap about mixtures, and we're going to take a look at their properties, etc. Nothing that is super different from what I've learned before in lower sec. So in the first part of this video, you're going to learn about the definition of an element, you're going to learn about metals, non-metals, you're going to look at the physical properties. And we're also going to look at compounds, right, as well as mixtures, and through the whole chapter, we'll learn about the differences between elements, compounds, and mixtures. So let's start with elements first. Now, elements, interestingly, right, for those of us who watched the anime called Avatar, right, The Last Airbender, you will be introduced to this concept called elements very early on, right? In fact, these elements actually are quite consistent with various cultures around us. So if I bring you back a bit to the past, right? Just a little bit of history, right? Actually, in the ancient times, this concept of elements already existed, right? So whereby there were all these Chinese astrologers, right? They actually think that all the substances in the world were made out of 5 elements. They call it earth, fire, water, air, and metal, right? So these were how they perceived elements to be, right? But of course, in the Angmo side, right? So in the 18th century, the various scientists have also come up with various theories to understand about this concept of elements, right? And for this particular person that you see over here, is also known as the father of chemistry. He actually came up with the concept that elements, in terms of the definition, are substances that cannot be broken down further by chemical methods. Now, this is actually what we still know today as a definition of elements. So throughout history, there's many more discoveries of elements that are being made. Some intentional, but more often than not, most of them are actually by accident, right? So in 1869, the first periodic table was actually developed by this Russian chemist. Okay, I'm not too sure if I'm pronouncing his name correctly. Dmitry Mendeleev, right? This was actually the first periodic table that you see on the right hand side. Looks totally different and looks very weird, right? So it looks different from what we have been used to looking at in terms of their very nice rows and rows of elements, but it actually looks like this in the past. Now, if you look at Mendeleev's periodic table, what is interesting is if you focus carefully, you realize that there were some elements that was indicated at question mark over here. And there's also one more question mark over here, and there were also some numbers here that has a question mark after that. Now, if you take a while to think about this, what actually happened then was when Mendeleev actually came up with this periodic table, he has actually already predicted that there will be elements that belongs to these question marks that you see over here. Now, this is pretty interesting, right? Because even without discovering the element, he can make the prediction. And that we know today because elements are in increasing number of proton number. So naturally, you should be able to find elements based on a certain proton number around the entire universe. Right? So that's where Mendeleev actually could come up with the theory. And then if you look at a second set of numbers here, which has all these question mark after the number, you realize that he was also not very sure about what this would mean. But for Mendeleev, just to let everyone know, these numbers that you see over here are actually the mass number, or what we call the nuclear number. Of course, in today's world, we know that this is not the correct way to label your elements. You should be looking at in terms of proton number, right? So these are just something that show you how chemistry or science actually changes over time. But none of the discovery is actually as epic as this one. So you're going to watch a video later on. This is actually about an alchemist known as Henning Brand, who actually discovered the element phosphorus. So phosphorus in the periodic table, you will find it and it will look like this. So the proton number is 15, the nuclear number is 31, right? And what is cool about this discovery was that it actually came about because this particular alchemist was so obsessed with this idea of what is known as a philosopher's stone, right? So he thought that this chemical is able to turn things into gold. So that's why he wanted to spend all his wealth, all his fortune. He used up all his savings, his wife's savings, in order to pump into this research. And he felt that it must be found in the human's urine, because urine is the only thing that, when you drink water, it's colorless, but it comes out as yellow or golden to him, right? So he actually bought a lot of urine from various people around the world, around the town, and then he actually bring it into the lab, his own lab, and he started to do all the separation, etc., etc. But that surprisingly actually allowed him to discover the element phosphorus instead, which is found in the human's urine, right? So he didn't manage to find a philosopher's stone, but this is just an example to show you how sometimes certain discovery happens by accident.
It's Hamburg, Germany. The year is 1669. Inside of a basement laboratory, alchemist Henning Brand is boiling gallons of urine to create the fabled philosopher's stone. Unbeknownst to him, the urine is about to lead to a truly world-altering discovery. During the Middle Ages, the philosopher's stone was the coveted discovery because it was believed it could turn ordinary metal to gold. In his quest to find it, Brand accumulated over 1,500 gallons of urine. He thought that by purifying the waste, the philosopher's stone would materialize in what was left. The process went like this.
1. Age the urine until an intense odor billows out of the samples. 2. Boil the urine until a white paste materializes. 3. Place the heated paste in a retort. 4. Gold will then drip out of the... Wait, what?
Okay, so it wasn't gold that emerged, but a solid white substance that glowed in the dark. This was big. This was bigger than big. His discovery was going to change the world. Brand had discovered phosphorus, one of the building blocks of life, making him the first person to ever discover a chemical element. But the thing was, he had no idea. He believed he had found a glowing philosopher's stone and named the substance phosphorus, meaning bringer of light. Brand kept his discovery a secret until he eventually sold his process to other scientists. It wasn't until after his death that he was given credit for discovering phosphorus, all by boiling urine in his basement laboratory.
So, definition. We have learned this before in lower sec, so it shouldn't be too hard for you. A pure substance that cannot be broken down into two or more simpler substances by chemical processes. And we know that elements, we represent them by their chemical symbols. And you can refer it to your periodic table, right? So for example, calcium is represented by Ca, capital C, small letter a. Phosphorus represented by a capital P. Mercury is a capital H followed by G. Sodium is a capital N followed by A. Now, you may be curious as to why some of these elements actually don't follow the same letters. For example, Mercury, why is the symbol Hg? Why isn't it Me? Right? Sodium, why is the symbol Na? Why isn't it So? Right? This actually has to do with, more often than not, the Latin names of these elements. Right? If you're curious, you can go online to search up. So this is our periodic table, right? So we know that in our periodic table, elements are arranged in various formats. This is actually what we call a group. So there's group 1, group 2, group 13, group 14, group 15, group 16, group 17, group 18. So in case you are confused, just take note that group is vertical. That means top down, right? From top to bottom. Now, horizontally, you also have these various rows that you see over here. Now, these are what we call period. Now, period are the horizontal ones. Okay, so basically, every element can be found based on how you arrange it over here. So, of course, in the periodic table, there is this staircase that you see over there. It actually separates what we call metals and our non-metals. So, the metals are on the left-hand side of the staircase. The non-metals are on the right-hand side of the staircase. Right? And then we have this very special group of elements in the middle block. These are called the transition metals. Okay, and of course, those that's nearby the staircase, highlighted in purple here, these are what we call the metalloids. Right, so in the next few pages, we are going to take a look at what exactly are metals, non-metals, as well as metalloids. Okay, do take note that group 1 is what we call alkaline metals. Group 17 is what we call halogens. Right, you'll learn about all these things along the way in this entire syllabus. And group 18 is what we call noble gases. So just some physical properties of elements, in case you've forgotten, you can also refer to your textbook, right? So metals, they have certain properties, right? They are shiny, they are mostly solids, that means they have high melting point and boiling point, they are ductile, and they are malleable, right? Whereas non-metals are usually dull, they usually are gases, they have low melting point and boiling point, and they are very brittle. Now, what about the middle one, the metalloids, right? So this one is the one that was shown over here just now. The metalloids has a bit of metal characteristics and a bit of non-metal properties, right? So if you look at it carefully, you realize that they are shiny, just like your metals. But they also have brittle, which is like your non-metals. So you realize that metalloids are usually a bit of both, right? That's why they actually fall within the staircase itself. Okay, so let's do a quick check on your own. Maybe you can use the periodic table, right, to actually go and find out what's the chemical symbol of these elements. You can pause the video at this point, right? Then after that, in about 5 seconds or so, we'll start to review the chemical symbol for each of them. Okay, so for magnesium, Mg, manganese, Mn, sulfur, S, silicon, Si, zinc, Zn, and then tin will be Sn. Okay, hopefully you got all of this correct. Now, let's take a look at this video now to see. This is a process about heating of sugar. So as you watch this video, do ask yourself if you think that sugar is actually an element. So sugar is inside this test tube now. Take a look closely. As you watch the video, observe what's the change. See what is happening. Think about what could be the process that the sugar is going through, and ask yourself what are some of the questions that you have in mind. Right, so based on this observation, what do you think? The sugar went from this kind of observation to this one that you see in the video. Do you think sugar is an element in this case? Why and why not? So based on this observation, we can actually conclude a few things. But before I go on to discuss about what it means, right, I just want to let you know that what happened just now when the reaction took place was there's actually the formation of what we call carbon and water vapor. So this was actually sugar. Then it actually became carbon and water vapor. So based on what you saw in this entire video, do you think that sugar is an element, right? And if it's not, what is your explanation behind why it is not, right? It's not just about writing yes or no, but trying to think about why is it not, or why is it an element, right? Hold that thought in your mind. We're going to take a look at a second video now to show about water and the reaction that it can go through.
If we connect an electrolyzer filled with distilled water to a source of direct current, we can observe a slow evolution of gases. After some time, we notice that the volume of the gas released at the cathode is double that of the gas formed at the anode.
what you see here is a process whereby the water actually got broken down into hydrogen and oxygen gas. So based on this statement that you see over here, and based on what you watched in the video, do you think that water is an element? Why and why not? Right, so that brings us to the next concept in this chapter about compounds. Now we know that compounds is actually a pure substance that's made up of two or more elements that are chemically combined in a fixed ratio. Now what would this mean? Right, we know that there's water, H2O, which means that it's made up of elements of hydrogen and oxygen, carbon dioxide, CO2, made up of carbon and oxygen, sodium chloride, NaCl, made up of sodium and chlorine. Now what you saw just now in the two videos was actually a process to show you that sugar and water actually could break down into simpler substances. So the correct answer for just now those two videos is that sugar and water are not elements, because elements cannot be broken down into simpler substances by chemical methods. But what I saw just now in the video, it proves that when sugar is being heated up, it actually forms something else. When water is being electrolyzed, it actually breaks down into something else. Right? So these are examples to show you why are they considered compounds. So do take note that fixed ratio of the compounds means that if it's H2O, it must always be H2O. You cannot just change the number that you see over there. If it's CO2, it will always be CO2. It cannot be CO3, it cannot be C2O4, etc. Right? The ratio must be fixed. If not, it will be a totally different chemical. So for example, there's this chemical called hydrogen peroxide, H2O2, is very different from H2O. There's this chemical called carbon monoxide, CO, is very different from CO2. In the next slide, we'll be taking a look at some videos to show us how exactly are compounds being made. Right, so in the video, you'll realize how different elements come together to react with one another, and then they form a new substance. Right, and through this, I hope you can recap a bit about what you learned in lower sec, that chemical compounds actually have very different physical properties from their constituent elements. Right, so let's take a look at the first video where it shows you how sodium is reacting with chlorine.
I took the sodium back out and I heated it a lot until it was molten red. This time, when I placed it back into the chlorine, it was a much more spectacular reaction. The sodium burned really bright and it turned my Erlenmeyer flask into a lantern. The test tube was coated in a thick layer of nice white sodium chloride. I tried to scratch off as much as I could, but it's honestly very hard and stuck very tightly to the glass. When it's poured out, you can see that this product is much cleaner than the last run. This sodium chloride was surprisingly fluffy, maybe because it wasn't contaminated with so much sand.
Okay, as you can see in the video itself, you realize that sodium is actually a silver, shiny looking metal, whereas chlorine is a yellowish green gas. Now when these two come together to react to form sodium chloride, it actually forms a white solid. Right? And sodium chloride, just to let everyone know, it's actually the salt that we use at home. You know, the one put on our fries, put on our fish and chips. Right? That salt is called sodium chloride. So from something that is dangerous like sodium metal, something that's poisonous like chlorine gas, you can actually make something that's edible that you put in your food on a day-to-day basis. Right? This shows you about how a chemical reaction can form a new substance that's very different from the original chemicals. Let's take a look at another video to see another reaction. So let's just do a quick summary. This was how magnesium looked like before, right? It is shiny, right, as a metal. So it's a grey solid that's over here, and after that, it actually became this white color looking solid, and this is what we call magnesium oxide. So this is what we observe to happen, right? Now, so as what you can see in the previous two videos, a compound has very different properties from the elements that form it, right? So for example, magnesium and oxygen that I mentioned just now, one is a grey solid, one is a colorless gas, but boom, together it forms a white solid, right? This is one of the characteristics of compounds that you need to take note of. Another thing that you need to take note of is that compounds can actually be broken down. So as what I mentioned at the a few minutes ago, sugar and water can be broken down. And what are the process that breaks them down? One is what I call thermal decomposition. This involves heating, right? So the word thermal means heat, and decomposition means to break down, right? So you are using heat to break down something, right? So that is first one of the methods they can use to break down compounds, right? The other one is electrolysis, right? So lysis means to split, electro means electricity. So this means that they're using electricity to break down something as well. So compounds can be broken down into simpler substances, but elements cannot. Okay, so let's do a quick check-in now to see that whether we are very clear about which are elements, which are compounds. Right, so maybe we can pause the video here as well and look through all these 4 questions and label next to them whether it's an element or compound. Alright, let's take a look at the answer now. So for the first one, it's actually a compound, followed by element, followed by element, followed by compound. So what do you realize over here is about whether they have different symbol or not. So it's not about how many, it's not about how many of the elements do you see over there. So for example, oxygen, even they write O2, but it's both O. So this is considered an element. It's not a compound. CO is one carbon and one oxygen. Different elements, so it is a compound. Okay? Now we move on to the last part, which is about mixtures. Now mixtures is made up of 2 or more substances that are not chemically combined together. Right? So this time round, it's no longer about, so to take note of a few things. It's not elements. So just now compounds, we were using the word 2 or more elements. Over here, mixture is 2 or more substances, which means that these can be elements. It can also be compounds, or you can even go more extreme and mix elements and compounds together. So it's not a case whereby it's always going to be just elements or just compounds or whatever, right? So do take note that there's a difference in terms of the definition, right? So what are some common mixtures that we know, right? Alloy is one example, right? So alloy is a mixture of metals with other elements. So there's steel, right? There's also brass, etc. There's bronze, there is stainless steel, for instance, and various different types of alloys. So are mixtures very different from compounds? Is there a way to really see what exactly are their differences so that we can compare them? Right, so in the next slide itself, we're going to watch a video. Okay, the video is a very old video, so the resolution is not very clear, and the sound is going to be quite humorous. When you play it later on, you know what I mean. So I'm just going to tell you what's going to happen first, so that you don't get too distracted by the video's audio. Okay, in the next video, you're actually going to see a mixture of iron with sulfur versus a compound of iron sulfide, right? So in the video itself, they're going to show you if you were to put iron, Fe, with sulfur, S, together as a mixture, and you were to use magnets or whatever, what do you observe, right? And if you were to do FeS, which is iron sulfide, a compound, if you put magnet around it, what do you observe, etc. Okay, so I'm sharing with you this thing first because as I go on to the next slide now, the audio is going to be quite distracting. Okay, so just watch and observe and try to make sense of the difference between a mixture and a compound. Alright, so as you saw in the video just now, basically when the magnet is placed over a mixture of Fe and S, what happens is that the iron foulings will be attracted and will be separated from sulfur. On the other hand, if you have a case of iron 2 sulfide, you realize that the compound is actually no longer attracted to the magnet. So what this tells us is that the physical properties of a mixture is actually similar to the constituent substance. That means in the case of iron and sulfur as a mixture, because iron is magnetic, when you have a mixture there and you put a magnet over, there's going to be some form of response. Whereas for a compound, the properties are no longer the same. Right? So as what you observed just now, iron is attracted in the mixture itself, iron is also attracted, but in the compound is no longer able to do so. Right? So what can you infer from this entire video itself is that physical property of a mixture is the same as the constituent elements. Physical property of a compound is different from the constituent elements. Now this is for most of the cases. Sometimes there can be some exceptions, but it's okay. As we go on to the exceptions, we understand, we exploit one by one. Okay, so based on what we have gone through so far, we are actually able to do a summary in this sort of comparison of compounds and mixtures. So for this one, actually it's okay to just refer to the textbook for the whole content, but just want to highlight the 4 key comparisons between a compound and mixture, but this is still similar to lower sec. Number 1, methods of separation. Compounds cannot be separated by physical methods, whereas mixture can be separated by physical methods. Compounds must be separated by chemical methods. Okay? Next, properties. Chemical properties are the same in the case of a mixture, but for the case of a compound, it will be very different chemical properties. Okay, so do recap what are these main 4 differences. Number 3, for mixtures, when they are mixed together, there is no energy change. That means energy is not given in or not given out or taken in, right? And for a compound, there is usually an energy change that's involved. It is similar to in lower sec as well. Last one, for a mixture, the composition is not fixed. That means you can have a lot of iron, very little sulfur, or a lot of sulfur, very little iron, depending on what you're mixing. But for a compound itself, it must always be a fixed ratio. So for example, in the case of the video that you saw just now, for FES, the ratio must always be ratio of 1:1. Once it's not the same, then it will no longer be the same compound. Okay, so take note of these differences between compounds and mixtures. Refer to your textbook, refer to your notes if you need a proper summary. Alright, and let's move on to the last part, whereby we look at the micro views of elements, compounds, and mixtures. Now, so we mentioned just now earlier about this thing called macro, submicro, and representational. And just now in the first part of the lesson, I was actually focusing on the macro bit, the left-hand side here. Now we are going to take a look at the micro part. We're just going to look in terms of the atoms or molecules or whatever you look in terms of the particles, so that we are all very clear in terms of an element, how it should look like. If it's a compound, how should it look like? If it's a mixture, how should it look like? Okay, so compounds, elements, right? Mainly, they are always made up of atoms. So these are the smallest particles of an element that can have the same properties of the element. Right? This is what we went through in the previous chapter on atomic structure. Right? Atoms of an element is different from that of another element. So the size will be different, the number of protons will be different, etc. So noble gases, your group 18 elements, they exist as what we call monoatomic elements. That means they exist as a single atom. So you will draw them out as individual atoms. But there are also some chemicals that exist as molecules, right? So molecules is a group of 2 or more atoms that are chemically combined. If they are made of the same atoms, we call it a molecules of element. So for example, O2, N2, Cl2, Br2, these are all elements because they are the same chemical, but they exist as molecules because you draw them out. That time it will be 2 circles, 2 circles, 2 circles, 2 circles, right? Because they are molecules. But molecules can also be made of different atoms. In this case, they will be compounds. So example will be like H2O, right? Example will be like CH4, CO2. They are also made up of, they're also made of atoms, but in this case, it's different chemical. Therefore, it will be considered a compound. Right? So atoms or molecules just means how it looks like. So in this case, it will look like this. In this case, it will look like this. In this case, it will look like this, for example. Right? So this is actually what particles means in terms of the micro observation. So in chemistry, diatomic means 2 atoms. Triatomic means 3 atoms. If it's more than 3, we usually call it polyatomic. Right? So these are just some examples that you see in your notes. Right? So ozone is triatomic, hydrogen is diatomic, and sulfur in this case made of 8 of the atoms is what I call polyatomic molecule. So in the compound, we mentioned just now in the video that compound is made of two or more elements that are chemically fixed together in a fixed ratio. So chemically combined together in a fixed ratio. This would mean that if we were to show you the micro view of a compound, you should be able to see at least two different types of the circles, right? So over here, in the case of the molecules, you see the one on the left-hand side, but you can also learn about this thing called ions, which in the next chapter, you're going to learn about ionic bonding, and you will look like the things on the right-hand side, right? But main thing is that it's two or more different ones. For a mixture, we went through in the previous part of the video that they are not chemically combined. This will mean that you shouldn't expect them to be joined together with different circles, but they can be in the same space. So a mixture can either be a mixture of elements, a mixture of compounds, or a mixture of elements and compounds. How could this look like, right? So maybe you take a pause over here now to try out this practice question on your notes, right? Have a go at this, then we will run through this in class to make sure that all of us are on the same page. It's very similar to what you have learned before in lower sec, right? Looking at the diagram, can you spot which of these are a mixture of elements? It can be more than one that you see over here. Which of these are mixtures of one element and one compound? That means one type and one type of compound. And which of these is a mixture of, different types of compound, right? So maybe just scribe down your answer here. We can run through these when we meet face to face. Okay? So mixture of elements, what could it look like? You'll see something that looks like this, right? It's not that you can only see two circles, you just see two types of structures that you see inside. So in this case, you see the two blue circles those are representing hydrogen. So each of the pair is actually a hydrogen over here. Right? So this is a H2, this is a H2, this is a H2. But I also see the single circle one, those are monoatomic. So these are our neon, because the noble gas, group 18, neon, neon. Right? So you can see that actually it's just two different types of elements. Mixture of compounds, right? In this case, you can be having a mixture of CO2 and also a mixture of H2O, right? So similarly, it's okay for you to have more than two things that you see over here. It's more about the types of it. So where you see two different types of compound molecules, okay? And the last one, mixture of one element and one compound. So you see over here, you can see H2 very clearly. These are the two blue circles. But you also see another one that's a bit bigger and is a compound, which is actually ammonia and H3. Right? Same thing, it's not about having only two structures, it's having about two types or more of structures. So in summary, these are some of the things that we went through, right? Atoms of the same element, it could be monoatomic, you see on the top left hand corner now, or made up of just the gray circle. It can be a molecule, right? So in the case of chlorine, Cl2, you'll see a structure that looks like this. For compounds, you'll see them as more than one type of circles joined together, right? And for mixtures, you'll see as a mixture of different types of structures, as you can see from this part of the notes. Okay, so with this, we have come to the end of the notes on elements, mixture, and compound. You realize that it's pretty much the same as lower sec, right? So now let's put this into practice with the worksheet that's been given to you. Complete that worksheet and be ready to submit it by the next lesson. Thank you.